हेलो, अस्सलाम वालेकुम। मेरी आवाज आ रही है?
यस सर।
क्लियर?
जी सर।
Okay. So let us start from where we left. So let me एक मिनट इसको एडमिट करता हूँ। तो let me share the whiteboard. अरे एक मिनट। Okay. अरे कहाँ गया ये? Okay. हाँ पीरज़ादा यास क्या है? तुमने हाथ उठाया। और ये आवाज कहीं से आ रही है, वहां जरा म्यूट कर लो। अगर बच्चे आसपास कुछ भी नहीं, बच्चों की आवाज आ रही है। एक मिनट। ओके, कल हमने थोड़ा शुरू किया था with the definition of a normal linear space. So a normal linear space was a vector space along with a norm. So let me write it down again. Normed linear space. As you can see, it's a linear space. Linear space matlab vector space, and you also know that a vector space is defined over a field. It's a set that is defined over a field, in this case which we represent by K, and in our particular case K would be either the set of real numbers or the set of complex numbers. So now you have a linear space over a field, and you also have a function called norm defined from this X, linear space X, to non-negative real numbers with certain properties. Of course, we've got norm of X. It would be 0 if and only if X is 0. Then you have got the homogeneity property, alpha X of norm of alpha X is mod of alpha into norm of X. And of course, the triangle inequality, X plus Y is then equal to norm of X plus norm of Y. तो ये है हमारी definition. Once you have a linear space along with this function, we call it a normal linear space in short. And we also know that every normal linear space is a metric given by the norm. And metric is defined with the help of norm like this. dxy is equal to norm of x minus y. And since it is a metric space, we say it's a complete normal linear space if it is complete with respect to the metric given by the norm. And we call it then a complete normal linear space is called a Banach space. Means it's a normal linear space and every Cauchy sequence in X converges inside X. And then we did some examples of normal linear spaces, and in particular, we did say Rn, Cn under different norms. And by that I mean Rn is the n tuple of n tuples of real numbers, and it's a vector space under pointwise operations. Same is the case with Cn. Same is the case with a sequence space. So let us move ahead and take more examples. And okay, let us today do examples other than these n tuples, which are simpler. Okay, first one. Should I write it here or should I go? I will go to the next page. Okay. So let us look at some examples. Now, L's infinity as the, what do you call it? Subscript L infinity is set of all scalar sequences, not n tuples. Now we are dealing with, an infinite set of numbers, possibly infinite set of scalars. Now, xi belongs to k. It's a sequence of scalars such that there exists a positive number, m positive, such that xi is less than m for all I greater than equal to 1. Now, it's a collection of all bounded sequences. Then I can also think of what we represent by C. C का मतलब है all scalar sequences. Now we are going to deal with these sequence spaces. Xi belongs to K such that now we're talking about convergent sequences. So convergent sequence limit Xi I approaches infinity exists. It converges. All convergent sequence of scalars is C. Then I can think of C0. It's x1, x2, so on and so forth. Xi are again scalars such that limit xi approaches infinity, xi is equal to 0. And in all scalar sequences that converge to 0. Then is another space, C00, another example. And we will take them one by one. It is all scalar sequences such that, of course, xi are scalars, and there exists m belonging to the set of natural numbers such that xi is equal to 0 for all I greater than m. And after a certain stage, this sequence becomes 0, 0, 0, 0, 0. Okay, so this is another space. Now let's think about these 4 examples for a minute. Now, first thing is L infinity a vector space under pointwise operations? By pointwise operations means, suppose I've got 2 elements xy belonging to L infinity, right? Then, of course, x plus y would be defined as, of course, x would be a sequence, so it would be x1, x2, so on and so forth, plus y1, y2, so on and so forth. And we declare the product to be the sequence x1 plus y1, comma x2 plus y2, so on and so forth. And of course, similarly, a scalar multiple of a sequence would be alpha into, of course, x1. We just multiply this scalar with each of the components of the sequence. हाँ, यहाँ पे थोड़ा सा हम कर रहे हैं. यूजुअली आप सीक्वेंस के लिए कर्ली ब्रैकेट्स यूज करते हो, लेकिन यहाँ पे हम राउंड मतलब पैरेंथेसिस यूज करते हैं. दैट इज द मतलब उससे कोई फर्क नहीं पड़ता. यू नो व्हाट्स अ सीक्वेंस, है ना? A sequence is a queue of numbers. You know, we must know which is the first one, second one, third one. It's queue of scalars. That's why we sometimes call it as a function from set of natural numbers to the field k, जहाँ पर ये number exist करते हैं. So sequence can also be thought of as a function from the set of natural numbers to the set of real numbers or set of whatever your sequence is. Now, since we are dealing with sequences of scalars and our k field is either real or k, a set of real numbers, field of real numbers, complex numbers, the function would be accordingly would have that range. Okay, so under these two operations, is this a vector space? Let us take L infinity. Let's call me this 1, example 2, example 3, example 4. So x belongs to L infinity, y belongs to L infinity, means they are both bounded sequences, right? So bounded sequence ka matlab, there exists an m positive. So there should exist. So therefore I can say that xi जो है, xi जो component है, xi is less than equal to some, less than, strictly less than, or less than equal, doesn't matter, for all I greater than equal to 1. Similarly, yi must all, because x and y both are inside this, so it must satisfy this property. So it would be some m prime less than equal to some m prime for all greater than or equal to 1, then you can easily see that xi plus yi is less than or equal to modulus of xi plus modulus of yi, which would be less than m plus m prime for all I greater than or equal to 1. I can say then xi plus yi is less than, say, let's call it this m, mu, for all I greater than equal to 1, where m plus m prime is this number mu, a positive number. Mu would be equal to m plus m prime, which would be positive. So it means it satisfies this x plus y के जो components हैं यहाँ पे, they satisfy the condition to belong to the set of L infinity. So it is closed with respect to addition and of course scalar multiplication by the same reasoning. So L infinity is a linear space. It's a vector space. Now same applies to convergent sequences. If I take a convergent sequence and then add another convergent sequence, then what you have is sum of two convergent sequences is again a convergent sequence, because you can distribute the, no, because चलो मैं यहाँ लिख देता हूँ, because limit xi plus yi is equal to limit of xi plus limit of yi for scalars. This is true. So if one converges, another converges, then their sum also converges. So again, the same reason, this is a vector space, this is a vector space, this is a vector space. Because if a sequence converges to 0, another sequence also converges to 0, then of course their sum would also converge to 0. By the same reasoning that limit would distribute over vector addition and scalar multiplication. Furthermore, if you look further is in this set, every convergent sequence is bounded. So C is a subspace of L infinity, right? And every sequence that converges to 0 is also a convergent sequence. And furthermore, if something has got, after a certain stage, a sequence becomes 0, then it must converge to 0. What I'm trying to say, so we have this relation. C00 is a subspace of C0, which is a subspace of C, which is a subspace of L infinity, right? तो अभी तक हमें सिर्फ ये मिला कि ये linear spaces है, ये vector spaces है. Now, can we define a norm meaningfully on L infinity? L infinity पे हमें norm चाहिए, वो, now remember again what is L infinity? It is all sequences, let me note it by x, such that xi belong to my scalar field over which they are scalars, either real numbers or complex numbers, okay? And there exists some positive number m such that xi is less than m for all I greater than or equal to 1. So I can give an example. You can take a sequence, say here 1, 0, 0, right? You can also take an example, say 1, 1 by 2, 1 by 3. Now this is a bounded sequence. You can take so many examples. Huh? You can also take an example 2, 3, 5, 1, 1 by 2, 1 by 3. Now these are all bounded sequences, not the way they are going. Of course, this would all these numbers are less than, say, 1.1 m in this case. Same applies here. Of course, this would be less than 5. So these are all bounding sequences. These all elements belong to L infinity. Now, can we define a norm on it? Of course we can. The reason is every bounded set of real numbers has a supremum, because so if you take a bounded sequence, you define a norm for x like this. Norm of x would be defined as supremum of this set of numbers, because this exists as a real number, and since it is mod, so it is a non-negative real number. So you take the supremum of the set, because these are bounded sequences. That's why we put the condition that it's a bounded sequence. So this is a well-defined thing, because every bounded set of real numbers, this is a bounded set, so there must be a supremum. So we let that supremum to be the norm of x. Just if, for example, norm of this would be here, norm of x would be 1. Here also norm of x would be 1. Here the norm of x would be, of course, 5. If you take this sequence. So it's a well-defined thing under this norm star. And that way, L infinity becomes a normed linear space now under this norm. Right? Do I need to show that this is indeed a normal linear space? And you have to show that properties of the norm. पहला तो obvious है कि norm of x जो मैं last time हमने किया था एक जगह बिल्कुल वही repeat करना. This would be this is equivalent to saying that supremum xi I greater than equal to 0 is 0. और जैसा कि हमने last time argue किया था कि अगर set of numbers है non-negative numbers उनका सबसे बड़ा 0 है, it is only possible if xi is equal to 0 for all I, which is possible if and only if xi is equal to 0, which is the same thing as this sequence x must be a null sequence. So a null sequence का ही जो norm है वो 0 होगा. Then, of course, needless to say, alpha x would be modulus of alpha into norm of x, and the triangle inequality is obvious here. For the same reason that we did in the case of Rn, everything would extend. So now I can say L infinity is a normed linear space with the norm star. The norm is defined here. The next question, and how about C? अगर कोई convergent sequence है under the same norm, C is a normal linear space. So is C0. So is C00 जो हमने इससे पहले example दी थी previous page पे. Under the same norm, क्योंकि ये भी तो bounded sequence है, ये भी तो bounded sequence है, तो उसका भी supremum होगा, उसके लिए भी ये norm defined है. So अगर उसके लिए ये norm defined है, so I can say now C is a subspace as a normal linear space. It's itself a normal linear space under the same norm of L infinity. So C0 is a subspace of C, which contains C double naught. So we have now got a collection of subspaces and spaces under the normal linear spaces. And we can just move ahead. Now we can ask a question. Is L infinity complete? Is L infinity under this norm? No. When I say L infinity, we usually denote मतलब L infinity का मतलब ये norm है. इसको हम यहाँ छोटा सा infinity भी लगाते हैं. Norm of छोटा infinity मतलब ये वाला norm है. Supremum I greater than equal to 1. इसको क्या हो गया? Okay. The modulus of xi. ठीक है. So is L infinity complete? Does every Cauchy sequence converge there? Now, when I'm talking about a sequence in L infinity, I'm talking about a sequence of sequences because L infinity is a collection of sequences. Now I'm saying a sequence inside this space. So I'm talking about a sequence of sequences. So we will denote a sequence of sequences by xn is equal to x, जैसा कि मैंने शायद कल कैसे बोला था मैंने, यहाँ मैंने 1 रखा था, यहाँ n, यहाँ 2, यहाँ n, यहाँ 3, यहाँ n. So only thing is I have जो individual sequence का जो अपना मतलब मेरे कहने का मतलब है ये वो sequence है. जब मैं ये कह रहा हूँ तो I mean this sequence. It's a sequence of sequences. By that I mean first sequence of this sequence is x1 1, x1 2, x1 3, so on and so forth. दो indexes होंगे. एक तो sequence का अपना, दूसरा sequence का sequence चूंकि है, because it's a sequence of sequences, so it would be x21, x22, x23, and so forth, and then x3 would be another sequence, x31, x32, x33. मतलब उतना भी मुश्किल नहीं है, तुम लोग कर सको, ठीक है? So now, so I want to show that L infinity is complete under this norm, that every Cauchy sequence converges inside L infinity. So let us start. So let x sub n be a Cauchy sequence in L infinity. So it implies that for any epsilon positive, Cauchy की definition, there exists some n naught, right, belonging to the set of natural numbers, such that norm of xn minus xm infinity is less than epsilon for all nm greater than n naught. So let me just separate this. यहाँ से ये इधर से, ठीक है ना? Now I want to keep this on the right hand side here. So just imagine if xn is this, what would be xn? xm का मतलब होगा, इसके components क्या होंगे? It would be xm1, xm2, so on and so forth. और जब मैं इनको subtract करूंगा तो point wise करूंगा, तो it would be इसके xn minus xm जो होगा, it would be xn1 minus xm1, xn2 minus xm2, so on and so forth. So I just apply. So it implies that अगर मैं यहाँ पे तुम्हारी ease के लिए इसको लिखूं ऐसे, means xn1 minus xm1 पहला component, then xn2 minus xm2, so on and so forth. इसको यहाँ बंद करते हैं. This is less than epsilon for all nm greater than equal to n naught. Greater than n naught. So which implies that by definition, जो norm की definition है, you take the supremum of the components. So it means it is supremum I greater than equal to 1 modulus of xni minus xmi is less than epsilon for all nm greater than n naught. Now again, supremum of a set of non-negative numbers is less than epsilon. सबसे बड़ा less than epsilon है, तो इसका मतलब सारे के सारे less than epsilon होंगे. यानी मेरे कहने का मतलब है x sub ni minus xm sub I is less than epsilon for all nm greater than n naught and for all I bigger than equal to 1. ठीक है? अब मैं क्या करूंगा, अगर तुम्हारा ध्यान इस पे है जो मैंने यहाँ लिखे थे ना, जिस तरह से मैंने पहली 3 टर्म सीक्वेंस की, तो what you would see is that if I fix n or m, I run through i's, है ना? Right? But if I let n run, the subscript run, so I run through first term and second term of, मतलब as I is fixed and let nm go to infinity, I would go along the first column or the second column of here. I'm going in this way, which is also a sequence, what I'm trying to say. So I can think now, अगर मैं थोड़ा clever हूँ, I can think now this is a sequence of numbers. अगर मैं columns लूँ, पहला column, दूसरा column, तीसरा column. Now this is a sequence of numbers. This is a sequence of numbers. This is a sequence of numbers. हाँ बोलो. हाँ क्या है? Hello. Abdullah Arif. हाँ, तो मैं क्या कह रहा हूँ? Now, if we look at this picture, every column can be thought of as a sequence of numbers. If I go downwards, which means if I fix I and let n and m range, so then what would happen is that it would be a sequence of scalars, which means what I'm trying to say is this. Let n run and keep n fixed. It implies that by definition, this xni is a Cauchy sequence of scalars for each fixed I. I hope ये तुम समझ सको. N run करने का मतलब नीचे वाला subscript run हो रहा है. 1, 2, I is fixed. So I am saying now this itself, this and again, this is again a sequence. This is again a sequence. And when I look at this particular inequality, it means that if I am fixing I and letting n run, I get a column of these sets. And each of the columns by this inequality implies that this is a sequence of scalars. So now this is a sequence of scalars here. this is a sequence of scalars, this is a sequence of scalars. So each of the columns becomes a sequence of scalars. And we know that they lie inside the set of real numbers or set of complex numbers which are complete. So for each I, let me again write it, xni is, for each I greater than equal to 1, is a sequence of scalars and a sequence inside K. And K is complete. K is complete. So which implies that xni converges to some. अब मैं यहाँ थोड़ा सा गड़बड़ करूंगा, यानी मैं इसको ऐसे लिखूंगा xi. It would converge to some number for each I as n approaches infinity, where this xi is inside K, because K is complete. तो मेरे कहने का मतलब है जो मेरी सीक्वेंस ऑफ सीक्वेंस थी, पहली सीक्वेंस थी मेरी x11, x2 नहीं x12 ऐसा था ना, दूसरा थी मेरी x21, x22, so on and so forth, and then x31, मैंने क्या लिखा, हाँ ठीक है, x32, so on and so forth. इसी तरह से यहाँ भी ये सीक्वेंस जा रही हैं. What I'm trying to say by our assumption, अगर ये sequence of sequences Cauchy sequence है inside L infinity, then this is a Cauchy sequence of scalars. This is a Cauchy sequence of scalars. What I'm saying now, then it must converge to some number, say x1. It must converge to some number, say x2, as n approaches infinity. And this must, मतलब इसी तरह से यहाँ पे एक और सीक्वेंस होगी which would converge to some x3, जिससे मैं एक और सीक्वेंस क्रिएट कर सकता हूँ. So that's the idea. और मैं दिखाऊंगा then under the same norm जो original sequence मैंने ली थी Cauchy sequence, it must converge to x1, x2, x3, and this must belong to L infinity, which would finish the proof that the L infinity is complete. So having done this, so let's move ahead. Okay, we show that xi, I runs from 1 to infinity, belongs, I have to show that it's a bounded sequence, right? No problem. So let me call this sequence x. Okay, I have to show that this is a bounded sequence, and I also have to show that xn converges to x, and I'm done. तो उसके लिए मैं पिछली वाली एक इक्वेशन थी, वो ये, let me write it again. Now xni minus xi, so let me, okay, I have got limit n approaches infinity, x ni is equal to xi. ये यहाँ के मतलब इसका मतलब यही है ना, इसका मतलब यही है. So which means that, so I also have another inequality. इससे पहले जो xni minus xmi is less than epsilon for all nm greater than some n naught, and for all I greater than equal to 1. Let me call this, ये पिछले पहले भी मैंने लिखी थी, चलो, let me call this star. अब ये star inequality है. If I let this m approach infinity, now letting m approach to infinity, what do you get? You get, as, because this is true for all m bigger than n naught. In particular, जब मैं m को approach करूँगा infinity, this would be still true. And as m approaches infinity, this would become xi. So I would have xni minus xi is less than epsilon for all n greater than n naught and for all I greater than equal to 1, which would imply, अगर सभी है तो इनका सुप्रीमम होगा, तो which would imply that norm of xn minus x is less than epsilon for all n greater than equal to n naught. Okay, अब ये करने के बाद xn minus x, तो पहली बात तो ये हो गई कि जब मैं ये लिख रहा हूं, it means xn minus x जो है उसका it is less than some number, so it means it's a bounded sequence, है ना. दूसरा ये कि xn converges to x, तो so इसको अगर मैं लिखूं, चलो नेक्स्ट पेज पे जाते हैं, it implies that xn converges to x and xn minus x belongs to L infinity. It's a bounded sequence because it is less than some number after a certain stage. Okay, but I had taken a Cauchy sequence xn inside L infinity. So xn belongs to L infinity and xn minus x belongs to L infinity. But L infinity is a vector space. So x equal to x minus xn minus x. Oh, sorry. Xn minus x. So if you have two numbers inside L infinity, their difference is also inside L infinity. So it means x belongs to L infinity. So I am done. तो एक तो ये हो गया. So xn approaches x, this sequence, which belongs to L infinity. So I had a Cauchy sequence, an arbitrary Cauchy sequence inside L infinity, which converges inside L infinity, which implies that L infinity is complete. So now I can say that L infinity under the norm, अगर जो इसका norm है, जो मैंने define किया था bounded sequence के लिए, वो ये था norm, इसको हम बोलते हैं sup norm, और यहाँ छोटी सी infinity लगा देते हैं. Supremum I greater than equal to 1 modulus of xi. अगर ये norm है, then this is a Banach space. ठीक है? Now I want you to check the same for C. क्या sequence of convergent sequence, again convergent sequence होगी, and C0 and C00. Home assignment. Check completeness of the following normal linear spaces. Almost identically तुम कर सकते हो, लेकिन मैं नहीं बताऊंगा इसमें से कौन है और कौन नहीं है. ठीक है? वो तुम वरना मतलब तुम थोड़ा अगर मेहनत करोगे खुद से तुम्हें पता चल जाएगा. Anyways, okay. So we did an example. इसके बारे में किसी को कोई क्वेश्चन है? थोड़ा सा इसमें ट्रिकी है ना वो, लेकिन अगर जिस तरह से मैंने दिखाया ना, we are saying कि अगर ये वाली सीक्वेंसेस फिर कन्वर्ज करेंगी, ये जो कॉलम सीक्वेंस और जो रिजल्टेंट सीक्वेंस हमें मिलेगी उसको इन नॉर्म, ये जो हमारा Cauchy सीक्वेंस है वो भी कन्वर्ज करेगा. So that was the trick that we used. Okay, so now we have got a good set of examples, है ना? So sequence spaces हमने की, which are normal linear spaces, and some of them are Banach spaces. How about another collection of sequences? So let me talk about LP sequences. P is greater than equal to 1. LP का मतलब है all scalar sequences, x1, x2, so on and so forth, such that xi belongs to k and summation xi raised power p, I runs from 1 to infinity, is less than infinity. हम इसको बोलते हैं pth power summable sequences. यानी अगर हम उनको pth power लें उनके मॉड्यूलाई का, तो फिर उसको सम करें तो वो मतलब वो as a series converge करेंगे. मतलब which is the same thing that they are summable sequences. For example, I can think of L1. क्योंकि p is greater than equal to 1. L1 का मतलब क्या होगा? All sequences of this type. xi belongs to k. They are scalar sequences and summation I runs from 1 to infinity. Modulus of xi is less than infinity. Right? इसी तरह से L2. L2 का मतलब होगा x1, x2. क्या बात है? xi belongs to k and summation I runs from 1 to infinity, xi ka square is less than infinity. For example, we can think of summable sequences, जैसे जिनको हम बोलते हैं जो as series converge करेंगे. For example, n1 में ये belong करेगी 1, 1/2, 1/4, 1/8, so on and so forth. Now this is a summable sequence, right? This is a summable sequence. L2 में कौन belong करेगी? इसका कोई member मुझे बता सकते हो? और भी members हो सकते हैं. I can take anything. मतलब this is also a summable sequence. So is this 1, 2, 3, 0, 0, 0. So is this, I can think of this 1 मैं और लिख सकता हूँ लेकिन मैं लिखना नहीं चाहता चलो ओके चलो उसको मैं आगे करूंगा L2 की कोई एग्जांपल मतलब जो ऑफ कोर्स L2 की एक एग्जांपल ये हो सकती है ये सीक्वेंस अगर मैं लूं 1 1 by 2 1 by 3 1 by 4 this belongs to L2 because if I take summation 1 by n square है ना मतलब मेरा xi ये है ना xi चलो मैं ऐसे लिखता हूँ here xi is equal to 1 by I. So if I take summation xi square, so it would be summation 1 by I square. और mod का भी वही होगा of course क्योंकि square है. So I runs from 1 to infinity. We know that this converges. है ना? This converges in fact for, I could have taken any peak bigger than 1. But this does not belong to L1. Why? Because summation 1 by I is divergent. If I just sum these numbers here, if I sum these numbers here, then it would be infinity. But if I sum their squares, it would be finite. So it would belong to L2 because it is square summable, but it's not summable. So there is something here which is not here. So in fact, you can easily show that L1 is properly contained in L2 is properly contained in L3. So ये भी एक home assignment है simple. शायद notes में मैंने की होगी. So on and so forth. तो अगर इस तरह से है, L1 would always be a proper subset of L2 and a proper subset of L3 because every summable sequence is square summable, but every square summable sequence is not summable. जैसे example है ये. It is square summable, but it's not summable. So we are moving a little ahead. So now let's take this p to power summable sequence. LP is now, of course, P is greater than or equal to 1. So you have got a sequence x1, x2, so on and so forth. Xi's are my scalars and summation xi raised to power p, I runs from 1 to infinity is less than infinity. It's finite. So it's a p-th power summable sequence. Now the question is it a linear space in the first thing? If I take two sequences that are p-th power summable, say x equal to x1, x2, so on and so forth, this belongs to say LP, and y equal to another sequence, let's call it y1, y2, it also belongs to LP. Does x plus y belong to LP? And is x plus y also a p-th power summable sequence? And remember, इसका LP में होने का मतलब ये है, ये क्या अब आ रहे हैं लोग? Okay, कि summation xi raised power p is less than infinity, and इसका मतलब है कि summation yi raised power p is less than infinity. ठीक है? So does x plus y? Now what is x plus y? It is basically x. It is simply x plus y is nothing but x1 plus y1. ये शायद अभी बंद हो जाएगा, फिर हम वापस join करेंगे. So this is x plus y. So is this p to the power summable? And we should have summation x. We should have what? Summation xi plus yi. अगर ये इसमें belong करती है, वो हमें इसको check करना है. Raised power p क्या less than infinity है कि नहीं? Right? But I know something for p greater than or equal to 1. I know this Minkowski inequality. If I take 1 by